Good afternoon, I'm Norman Wildberger, and we are in lecture 7 of this course on the history of mathematics. We're going to talk about analytic geometry and the continuum. So we are now in the European section of our subject, and the heroes, main proponents of this period are the French mathematician Pierre Fermat, lived from 1601 to 1665. René Descartes, soldier, philosopher, mathematician, 1596 to 1650. And Newton, 1642 to 1727. Now, the 17th century, so the 1600s, were a very fertile period, and these gentlemen and some others contributed to one of the really major advances in the history of mathematics. And in my opinion, second only to the introduction of the Hindu Arabic number system, what happened in this period is probably the second most important development. So what we had here is the introduction of coordinates into geometry in a systematic way, thereby unifying aspects of algebra and geometry. So this is a very important development, and it sets the stage for calculus, which was to follow shortly thereafter. Now, when we look back at history and say, well, when were coordinates first introduced, one can look and find examples in the ancient world of coordinates being used. So the ancient Greeks used coordinates in certain situations. So Hipparchus, who was an astronomer and one of the founding fathers of astronomy, already introduced coordinates for the night sky, for the sphere. And Apollonius also, who was more a geometer, but he was also an astronomer. But he was particularly known for his work on conics. So he introduced coordinates for a conic. And let's just mention briefly Apollonius's point of view. So when he was studying, for example, an ellipse, we've already talked about conjugate diameter. So we saw that if you take any chord and you look at all the chords parallel to it, then the midpoints of those chords form a diameter. And if you then look at all the chords that are parallel to that diameter, and you take their midpoints, then you get a conjugate diameter. And so what Apollonius found very useful is to use these conjugate diameters as a reference frame to study the conic. So use these as a basis for coordinates. So, for example, he might say that if you have a point up here, you can express it in terms of maybe a coordinate x in this direction and a coordinate y in this direction. And then you could express the ellipse as an equation involving x and y, and you get an equation that's not so much different from the one we use now. But this approach really started with the curve, started with the ellipse or the hyperbola or whatever conic it was, and then created a basis that depended on the curve. So he started with the curve and then found an appropriate or useful set of coordinates to describe that curve or to solve whatever problem he was interested in. So the curve came first, and then he adapted some coordinates to that particular situation. In the European period, in the medieval period, there was a mathematician, Oresme, who lived in the 1300s, who also introduced something a little bit more towards the modern framework. He sort of had the idea of x's and y's expressing relative changes of things. So he had a sort of an idea of position, time, velocity, representing those things graphically. But he didn't have a very developed algebra at that time, so he wasn't able to go too much further. So it was really Fermat and Descartes, these two French mathematicians, who introduced the coordinate system that we now use all the time. And the idea now is, so Fermat and Descartes, is you create a coordinate system and then with respect to that coordinate system, you can study various different curves. Then study curves in that system. And both of them are really responsible for this idea, although Descartes ended up taking the idea further. Fermat was also interested in other things, particularly more interested in number theory. But from their work, we now have the standard picture that's taught in schools everywhere, where we have two axes, x and y, and where the two axes are labeled by numbers, not just integers, but also fractional values, or possibly even irrational values. So we think of all the numbers that we can think of as kind of lying on this continuum: natural numbers, integers, fractions, negative numbers, and irrational numbers too. And we have two such coordinate systems, one in the x direction, one in the y direction. And then the point is that if you have a point in the plane, that point in the plane can then be identified or specified by its x and its y coordinates. So there's an x coordinate and there's a y coordinate, and so we can write A as the pair x, y. So we can go from a point, a geometric point, to an ordered pair of numbers. And conversely, if we have an ordered pair of numbers, like 3, 5, we can interpret that, we can think of it as representing a point in the plane. Now the advantage of this is that we can't, it's not just that we're going to be able to deal with points, but we can also deal with curves, more sophisticated things. So for example, if we take a line, perhaps that line there, going through the points 1, 0 and 1, 1 and 3, 2, and say, what was this next one, 4, 3, and then 5, 4, and so on. So all those points are distinguished by the fact that they're related by a linear relationship. So the points on the line are defined in this case by the relatively simple equation y equals x minus 1. So all the points that satisfy this lie on the line, and all the points that lie on the line satisfy this. And so we can end up thinking of the line as being represented by this linear equation in x and y. So lines are then represented in this picture by linear equations in x and y, such as the typical one, or the general one, being of the form ax plus by equals c. But then we can go further, and we can think of more general equations, not just involving x and y to the first power, but say higher powers. And then those will correspond to geometrical curves which are more complicated. So in particular, conics can be represented by, well, degree 2 equations in x and y. This was, I think, the great discovery of Fermat and Descartes, that the conics, or the conic sections of the ancient Greeks, had a particularly attractive and simple interpretation when we view them in this coordinate framework. Namely, they all become degree 2 equations. And by that, the general kind of equation would be ax squared plus bxy plus cy squared. And we're also allowed linear terms, so plus dx plus ey, maybe plus f equals 0. We put everything on one side. So that's the general degree 2 equation. It's got 6 free variables. And if at least one of these 3 is non-zero, then it's really of degree 2. If all these 3 are 0, then it's really just a line. But otherwise, it's a degree 2 curve, and it turns out to be a conic. So in some sense, this justified the ancient Greeks' preoccupation with conics, because now it was clear that there was some kind of natural hierarchy of curves, the simplest curves being the linear ones, degree 1, and then the next simplest being the quadratic curves of degree 2, and they're conics. So it's right and proper that the ancient Greeks studied conics. So let me just make sure we all understand this main idea. So the main idea is that if you have any polynomial equation in x and y, for example, you have some polynomial p of x and y equals 0, it represents a geometrical curve. Represents a geometrical curve, namely that curve whose points x, y satisfy the equation. So this now forms a very important link between pure algebra, where you're just studying some, say, polynomial in x and y, and geometry. So over here we have curves, geometrical curves in the plane, and over here we have essentially polynomials, or maybe more complicated functions later on too, but originally just polynomials. Polynomials in x and y. And here we have curves in the x, y plane. Now this correspondence is particularly important because Descartes, well, both Descartes and Fermat realized that finding the intersection of two curves is really equivalent to simultaneously solving the two equations. Simultaneously solving the two defining equations. So for example, if you have two lines, say the line y equals x minus 1, and perhaps another line, what would that be? Say that's 1, 2. So that would be the line y equals minus x over 2 plus 2, let's say. So we have two equations. Then where the two equations intersect, that's a point. That point, let's call it x0, y0, that's got to satisfy both equations. So to find that point of intersection means we have to solve the pair of equations, y equals x minus 1 and y equals minus x over 2 plus 2 for the intersection point x0, y0. And we can do that purely algebraically by making algebraic manipulations. And that, of course, was known to the ancient Chinese how to do that. The Chinese knew not just how to find the intersection of two lines, they knew how to find the simultaneous solution of a whole bunch of linear equations. And that process was elimination. So this technique of elimination, so the technique for solving systems of equations purely algebraically. It was rediscovered by the European mathematicians, but it really goes back to the Chinese. In fact, as Stilwell points out, is rather a nice remark, that the Chinese also knew not just how to work with linear equations, but also with polynomial equations. So this process of elimination also works, suitably modified, for some systems of polynomial equations. It's not so well appreciated, I think, today by undergraduates. So for example, without going into all the details, but if you have two curves, let's say x squared y cubed plus x y squared minus 3y equals 7, let's say, and another one, say x plus 1 times y to the fourth minus x squared y cubed plus y equals 2, just to make something up. Those two curves, algebraically, well, it might be a little bit hard to graph them, to find points. It would certainly have been hard in years gone by. These days our computers are quite good at drawing something like this. So it maybe the first curve, you know, looks like this, and maybe the second curve looks like that. Who knows? Okay. Then solving them simultaneously means that we're trying to find the places where they meet. So there they meet, and there they meet, and there they meet, and so on. Okay. And in Stilwell briefly discusses a technique that the Chinese had for taking a pair of equations like this and eliminating. And so their idea was, it's a lot like what you do with row reduction. You want to eliminate the highest power of y. So what you do is you take equation 1, and you multiply it, say, by x plus 1. So if you take x plus 1 times equation 1, and then you subtract x squared times equation 2, then as an equation in y, then the resulting combination, did I say that right? You have to have a y somewhere. Okay, if you have to have a y. Let's x plus 1 times y, let's say. So y times x plus 1 times the first equation. And then when we subtract them, then there will be no fourth power. So it gives us a lower degree equation in y. And if you do this carefully and you do it sort of systematically, you can then sort of successively keep on repeating and eventually get an equation where the y's are eliminated. And then you have just a remaining, perhaps a big polynomial in x that you still have to solve, but okay. So anyway, this idea of elimination using purely algebraic techniques can be applied to find geometrical places where curves intersect. So Descartes realized that you could solve a lot of classical problems going back to the ancient Greeks using this idea. The general idea of applying algebra systematically to geometry. And he wrote one of the most important books in the history of mathematics on the subject, and it's called, I guess, Geometry, La Géométrie of René Descartes. I suppose originally written in Latin, translated into French, and here is an English translation which I have. I'll just read you the first paragraph or two. So the geometry of René Descartes. He starts, any problem in geometry can easily be reduced to such terms that a knowledge of the lengths of certain straight lines is sufficient for its construction. Just as arithmetic consists of only 4 or 5 operations, namely addition, subtraction, multiplication, division, and the extraction of roots, which may be considered a kind of division, so in geometry, to find required lines, it is merely necessary to add or subtract other lines. Or else, taking one line which I shall call unity, in order to relate it as closely as possible to numbers, and which can in general be chosen arbitrarily, to find a fourth line which shall be to the other given lines, and so on, and so on, and so forth. Okay. So he's talking about setting up coordinates, so choosing a unity along one line, which you can do however you want. And then he starts talking about the relation of geometrical things to arithmetical operations with the coordinates that he's introducing. Descartes was an interesting character. He didn't get along quite with a lot of the other mathematicians of his time, with Fermat, Pascal, and so on. He didn't have that much to do with them. And so when he wrote this book, he was interested in sort of bragging a little bit about his accomplishments and making it sound quite good. So there are lots of places in here where he goes on about how this method is quite superior to anything that's gone on before, and how it sort of supersedes the work of the ancient Greeks, which was perhaps somewhat justified. I mean, really, it was a landmark book, this, and it really opened up very important new world, really. Descartes was a sickly young man, and so he ended up getting a habit of sleeping in the mornings. He was in the habit of sleeping in till late and thinking abstract thoughts while he was sleeping or while he was in bed. But eventually he became a soldier, and he was also an important philosopher. You probably have heard the phrase, "Je pense, donc je suis," which is, I think, therefore I am. His idea that, okay, thinking somehow proves existence. Okay, I'm not a philosopher, but his work is important in philosophy. And he was also a bit of a diplomat. He had good connections with the royals, different important people. And in particular, he had a correspondence with a Queen Christina, I think, from Sweden, a young, energetic queen who eventually persuaded him to come to Stockholm and give her lessons in philosophy. But she would get up at 4 in the morning, and so she insisted that he get there at 5 in the morning, and the winter in Stockholm is particularly cold, and this did not really suit Descartes' temperament, getting up at 5 in the morning in the cold Stockholm winter when he's used to sleeping in. And he ended up catching some cold or something and dying as a result. So, okay, but so let's talk a little bit more about conics. So, of course, the simplest conics are the circles. And if you have a circle and you know its center, let's say the center is x0, y0, and you know a radius, say r, then the equation of the conic is x minus x0 squared plus y minus y0 squared equals r squared. And when you expand that out, you get something with x squared and something with y squared, and then there's some other terms, some linear terms, dx plus ey equals c. So a circle has a rather distinctive equation. The quadratic terms are always an x squared and a y squared with the same coefficients and no xy term. So you can instantly recognize when you have a circle. An important problem that the mathematicians of the day recognized was, suppose you have a general conic. Suppose you have the conic 2x squared minus 5xy plus 7y squared, and then some other terms, 6x minus 5y equals 12. Okay, that's some kind of conic. But what kind of conic is it? Is it a hyperbola? Is it an ellipse? Is it a parabola? And how are we going to graph it? If it's a hyperbola, which way is it facing? Where are the axes? So they developed techniques for essentially changing coordinates. In other words, let's say the hyperbola really, or let's say it's an ellipse for the sake of argument, and it's like that. Then really what you want to do is you want to change coordinates so that you have a new coordinate system which is right through the center of the ellipse, in which the ellipse has a relatively pleasant form. So it might be of the form x squared over a squared, maybe something else, over 2 squared plus y squared over 3 squared equals 1, let's say. But now, not with respect to the original coordinates, but with respect to these new coordinates. Let's call them x1, y2. x1, y1, sorry. The original coordinates being x and y. So this is the kind of idea. We want to change coordinates in a suitable way so that the difficult equation becomes transformed to a more standard equation that we can quickly recognize and that we can graph relatively easily. So maybe we've studied ellipses that look like this, but we have no idea how to graph them when they're like this. So this was done, and they worked it all out, and this is still taught in high schools today. It's still a favorite sort of high school topic. How to change coordinates so that conics are in a standard form. And there's kind of a little bit of a trick that you can use to tell what kind of a conic it is by looking at these quadratic terms. If you make a little matrix with the 2 and the 7 down the diagonal, and then I think you have to put minus 5 over 2. You have to divide this one by 2. So if you look at that matrix, the x squared term, the y squared term on the diagonal, and the off diagonal terms being half of those ones there, then if you take the determinant of this matrix and call it D, then the sign of this determinant tells you whether it's an ellipse or a hyperbola or a parabola. So basically D bigger than 0 means it's an ellipse, and D less than 0, hyperbola, and D equals 0, sort of in between, is a parabola. So roughly speaking, the things that modern mathematics students learn in high school on conics would have all been old hat to Descartes. I don't think you could tell him anything that he didn't really know, or that he wouldn't say, yeah, that's pretty obvious. Okay. So that was in the 1600s. Okay. So what's the next step? We've understood lines, which are linear equations. We've understood conics, which are quadratic equations. Obviously, the next thing we should do is to understand cubic equations. And so they did, or they tried to. And just as there's a big step from lines to conics, so there's also a big step from conics to cubics. And it's a little bit unfortunate that in high schools you don't learn a little bit about cubics and this story, but algebraically it's quite a lot more sophisticated. So the next step is cubics. And cubic curves turn out to be interesting for a whole variety of reasons. Just as conics have many beautiful properties, so do cubic curves, but they're a little bit more advanced. So what does a cubic generally look like? Well, we know that we know this kind of cubic, right? Y equals some function, y equals, x cubed minus x squared plus 2x plus 5 or something. Okay. That's a cubic function. That's a cubic function whose graph always looks something like this. But just because you understand cubic functions does not mean that you understand cubic curves. A cubic curve is rather something which comes about from a polynomial in x and y of degree 3. This is a polynomial of degree 3 in x and y, but the y is only appearing in this one very simple place. A general cubic has the form, well, ax cubed plus bx squared y plus cxy squared plus dy cubed plus, and then, ex squared plus fxy plus gy squared plusghx plus iy plus hij plus j equals 0. That's what a general cubic looks like. So the powers of x and y can be mixed. The total degree has to be at most 3. That's defining the cubic. So what do those look like when you graph them? Well, Newton was very interested in that question. Newton, who's one of the heroes of the history of mathematics, or the history of science, we should be larger and say, and he classified cubics. He tried to do the same kind of thing as conics, conics being ellipses, hyperbolas, parabolas, and a few other degenerate cases involving lines. So he said, well, let's classify cubics. So he tried to classified cubics. Okay, and there's roughly, I don't know, can't remember, roughly around 80 on his list. He didn't quite, I think, get them all right. There were a few missing, okay, but so he missed a few. But we can't fault him too much because it's a lot of work. And how did he classify these cubics? Well, he took an equation like this, and he basically did the same kind of thing that we did over here with the conics. Tried to change coordinates to get the cubic in a particularly simple form. Just like we did with the conics, try to get it in a relatively simple form like this one. So we recognize that's a ellipse, or if there's a minus sign, that's a hyperbola. So his canonical forms were, well, there are various canonical forms. There's one that's like this form, axy squared plus by equals cx cubed plus dx squared plus ex plus f. And then there's some other forms. There's 3 other forms that are all more or less the same. xy equals ax cubed plus bx squared plus cx plus d. Or y squared equals the same kind of thing. Or just simply y equals the same kind of thing. Now, that's 4, not 80. But the point then is that once you've got it in one of those canonical forms, what ends up happening still depends on the relative nature of the right-hand side. You have to then look at the right-hand side and say, well, does this have 1 real root, or 2 real roots, or 3 real roots, or are the roots equal or not? Okay. So you then have to analyze the right-hand side. So what do cubics kind of look like? It's still not that easy to give an exhaustive picture because, well, it depends on the transformations that you allow. But examples of cubics are, well, ones like that we've already seen. That's an example. But there's also other ones that look like this. There's others that look like a blob, look like that. There's others that have some kind of cusp. So some different phenomena that happen. So here we have, this is called a node, where the cubic actually crosses itself. And here's a cusp where the tangents kind of come together. Get these 2 branches and they come together, have the common tangent. It's a cusp. And then there are other examples where you kind of have a blob that's separated from the main part. Not sure what that's called, a blob. It's probably not a technical term. But even this list is deceptive. If you write down a random cubic and ask your computer to graph it, it very well may not look at all like one of these. So for example, I wrote a paper some time ago where a cubic appeared and I had to graph this paper, this cubic, and it was something like something like that. So cubics can look like this. There's quite a variety to them. A rather famous cubic that was studied by Descartes is called the folium of Descartes. And it has the attractive equation x cubed plus y cubed equals 3axy, where a is some parameter that you get to choose. And the folium has the following graph. There's some kind of asymptote somewhere here, and then it comes in here like this, does a little loop, and goes back asymptotically to that. Should be a bit browner maybe. And this particular cubic, it's a nodal cubic because it has a node like this. It turns out that the nodal cubics and the cuspidal cubics are in fact somewhat simpler than the other ones. In what sense? Well, this kind of cubic, this can be parameterized. So if you work with these curves, eventually you want to ask the question, well, what exactly are the points that lie on here? I mean, how do I find an actual point that's lying on here? Okay, you have to solve this equation, but it looks like a cubic equation. You can't really solve it exactly. But some of the cubics can be parameterized, including the folium of Descartes. And in fact, general nodal cubics and cuspidal cubics can be parameterized. The other ones often can't. Or not so easily, let's say. Not rationally. It can be parameterized rationally, maybe I should say that. Okay. So here's a problem. Are we up to 19 now? Okay. Problem 19, and this is in Stilwell 7.3.1. Show that the folium has parameterization x equals 3at over 1 plus t cubed, and y equals 3at squared over 1 plus t cubed. So it means that if you plug in any value of t into that expression, you're going to get two numbers x and y, which lie on the cubic. And so you can happily generate as many points on the cubic as you want, just by substituting different values of t. It's not always the case that you can find lots of rational points on a curve. This is a very delicate question. Is how to find rational points. xy, where xy are rational numbers, on a given curve. And a famous example is the example x cubed plus y cubed equals 1. Which is a lot like, on the surface, it looks like x squared plus y squared equals 1. I remind you there were lots of rational points on the circle. Remember, I gave you formula for all the rational points on a circle. If you had a rational point on here, you could basically, sort of comes down to a number theoretical equation, n cubed plus m cubed equals p cubed for integers n, m, and p. And Fermat basically realized that this equation only has trivial solutions. There's a few obvious solutions where one of the variables is 0, but otherwise you don't have any solutions. So this curve, we have solutions x equals 1, 0, 0, 1. But no others. No other rational solutions. Of course, this is related to the famous Fermat conjecture, Fermat last theorem, that says that x cubed plus y, well, x to the n plus y to the n equals z to the n. If you generalize this curve to the nth degree, then this has no non-trivial integer solutions. So non-trivial meaning, aside from one of them being 1, aside from the case where one of these things is 0, and x equals y, z, or x equals minus z. This is Fermat's last theorem, but now known as the Fermat-Wiles theorem. Andrew Wiles having proved that some 10 or 15 years ago. Finally, after many attempts over the years by many people. So there's one very general question that we have to mention because it played an important role in the development of algebraic geometry, which is essentially the extension of this kind of work to higher curves. And this is a theorem it's called Bézout's theorem. Although probably Newton deserves a lot of the claim for it. Bézout's theorem says that if you have two curves, say p of xy equals 0 is of degree m, and q of xy equals 0 is of degree n, then these two curves should intersect in n m points. So for example, if you have n equals m equals 1, then we're talking about two lines. And two lines, okay, most of the time they meet in just exactly one point. If we have n equals 1 and m equals 2, it means one of the curves is a line and the other curve is a conic, maybe a hyperbola. Then we ought to have 2 points of intersection, because n times m equals 2.
Shouldn't it be a node?
Yes, you certainly think, well, it's true because of the way I've drawn it there, but if I drew the line in a different position, I could miss that hyperbola entirely. Well, you could draw that line right through the hyperbola. Where are the solutions then? Sorry?
They need to be complex solutions.
They become?
They need to be complex solutions.
Yeah, that's part of the way around this, is that people realized that they had to use complex numbers, had to find the other solutions in the realm of complex numbers. That's one thing that they had to do. They had to do something else too. What's another example? Suppose we have two conics, n equals m equals 2. So if you have one conic which is an ellipse like this, and you have a hyperbola, let's say, two curves of degree 2, then typically we have 4 points. If you have n equals 2 and m equals 3, so maybe we have a cubic. Okay, and then we also have a conic. Long skinny ellipse. Then we've got 1, 2, 3, 4, 5, 6. Okay, so this was a theorem only in quotes. This was really more a hope or a wished for thing. People knew that it sort of should be true, but it's pretty obvious that you can cook up counterexamples. For example, if I had chosen the ellipse to be this one right here, how is this thing intersecting the cubic in 6 points? Or even over here where you have two conics, what happens if you have two circles? How can two circles intersect in more than 2 points? Or even if we go back to the lines, what happens if you have two parallel lines? Where's the 1 point of intersection? Okay, so this is an attractive theorem, but it appears not to be true. It appears to be a theorem that's not true. But the 17th century mathematicians and then 18th century and then 19th century mathematicians, they started to think of this as, they started to think of ways of extending their understanding so that this theorem became true. And there were really two major developments that had to be done before it became true. So the true theorem requires, well, two things. It requires a projective point of view. What does that mean? Well, it means that you need to include points at infinity. There are points at infinity. There's an infinity somewhere, and these curves can meet at infinity, which is not visible in the plane, but should still be counted. So we have some kind of points at infinity, whatever that means. So the mathematicians, 17th century, 18th century, they realized that there should be these points at infinity. There was a lot of evidence for them. But exactly how to go about this is not so clear. So for example, here we want to think of these two parallel lines as somehow meeting at some point at infinity. So that's one of the things that was required. And the other thing that was required was complex numbers. So both of these were important developments. We're going to talk about projective geometry in our next lecture. But we'll take a break now, and I'll say a little bit about number systems in general after our break.